Okay, I think it's recording. This is on polynomials. Now, polynomials you know about. You've done a variety of different things. So these are notes. Polynomial functions. Now, with polynomial functions, you know certain things about polynomials. And they're not going to be a big deal, but just to let you know, a polynomial is any function p of x that's got something times an x to the power of something, and then it goes down. A different coefficient times x to something smaller, and it keeps going down all until you get to some coefficient times x to the power of 1 plus some coefficient times x to the power of 0. You don't even need to write the power of 0. This is a polynomial. Now, when you first started looking at polynomials back in grade 9 or 10, you looked at this definition, and the definition was important. This unit, what we're doing, is only going to look at 3 types of polynomials, and in fact 2 of them you've already done lots of. Okay? What we are going to look at is linear polynomials, or linear functions. We are going to look at quadratic functions, or quadratic polynomials. And we are going to look at cubic. Now, you've never really looked at cubic functions or cubic polynomials before. It's new to this course. But the linear you did in 10C, okay, and the quadratics you did in 20. Now, 20-1 or -2, it doesn't matter. But the quadratics you did in 20. And so I'm going to, these first 2 lessons are going to be about, one's going to be just about linear functions, just to make sure you recognize and remember the pieces of them. Tomorrow's is going to be about quadratic functions and the pieces of them. Just to review them. They're not really big deals, but they are just to review. Okay? So, going on, I'm going to put a new heading, linear functions, because that's what I want to talk about. The unit is on polynomial functions, but we're going to start talking about linear ones. Now, you last did these in grade 10. Can I move that up? You guys are okay? Okay. The thing you should know about linear functions is the graph of these functions. These functions will be straight lines. Okay? It's a straight line. It's a straight line at an angle, or a straight line horizontally, or in theory you could have a straight line vertically, but then it's not a function. But you have straight lines. Okay? And that's where it started with. Now, the other thing I want to say is they appear to go up or down by the same amount forever. They exist forever to the left, forever to the right of whatever part of the graph you see. And they just go up or down, depending on what it's doing, by the same amount. So over and up, over and up, over and up, over and up. Okay? And you can look at a variety of situations. Now, there's terminology that by this point in time in your math career, you've internalized. You do it without even thinking about it anymore, because it comes up in science. Okay? But an example would look like this, i.e., and here's where I want to talk about this, the cost of purchasing chocolate bars. You can tell I was hungry when I wrote this. The cost of purchasing chocolate bars increases as increases as you purchase more bars. Okay. So as you purchase more bars, it costs more money to buy those chocolate bars. Now the thing is, if we ignore the idea of like a volume discount, we'll start with this. Each bar cost. How much does a chocolate bar cost? $1.25? Did you say $2.50? Oh, for the bigger ones, I guess. Okay, I'm going to say $1 just because it's a nice round number. Actually, I'll say $1.25. Each chocolate bar costs $1.25. Okay? Sketch the cost of the purchase versus the number of bars purchased. This is a really simple situation. It's a goofy situation in some ways. But in all honesty, this is an example of a linear function in action. Okay? So if you were to sketch this, okay, the cost of purchasing chocolate bars increases, it's $1.25 per, sketching it, you know that you'd end up creating a grid. Now, you'd create the grid, and in fact, all honesty, all four quadrants of the grid exist. But this quadrant where I put the X, this quadrant, and this quadrant, there's nothing that's going to go in there because it doesn't make any sense. Because those are quadrants where either the cost or the number of chocolate bars would be negative. They don't make any sense. Mathematically, they exist. Mathematically, negative numbers work. But in this context, for the number of chocolate bars, it makes no sense. You have to start at 0. And you either buy 0 chocolate bars and it costs $0. And I'm just going to write 0, 0. Or you buy 1 chocolate bar and it costs $1.25. Or you buy 2 chocolate bars and it costs $2.50. And you get a series of points. Okay, or, and I'm not drawing this perfectly because I don't have grid paper, $3 or 3 chocolate bars and it costs $3.75. And so on and so on and so on and so on and so on. Okay? I could keep going and I could say there's a point later on where I buy 10 chocolate bars and they cost $11.25. No, they don't. $12.50. $12.50. Okay, and so on and so forth. And I could find various points. Now, if I was to look at this graph, if I was to sketch this graph would be a straight line. And you'd get a perfectly straight line. You could use a ruler. I'm not using grid paper, so my line isn't perfectly straight, and probably neither is yours. But nonetheless, that's what you've got. Now, in these functions, what I need you to remember is that in the context, it only exists where it makes sense for the context. In theory, mathematically, there is, I bought -1 chocolate bars for -$1.25. Okay? And that makes sense mathematically, but it doesn't make sense in the context. The linear function goes forever in each direction. And it goes up or down by the same amount. In this case, it goes up or down. Now, the thing I want to talk about this is these functions always have one x-intercept. They always have one x-intercept. Always. Every linear function will have an x-intercept. Okay? The x-intercept is where it crosses the x-axis. And if that's the x-axis horizontally, and that's the y-axis vertically, where it crosses that axis is right here, where x is 0. Now, in this case, the x-intercept represents the number of chocolate bars I can buy for $0. The number of chocolate bars I can buy for $0. That's what it represents in this context. Basically, what happens is at the x-intercept, the y is 0. Okay, the x-intercept in this case, how many chocolate bars I can buy for $0? 0. And I mean, you can figure that out logically, or really you can look at it at the graph. The other things that this graph always has is one y-intercept. Now, in this case, the y-intercept, or where it crosses the y-axis, is the exact same point. The next one I do, it's not going to be. But in this case, the y-intercept is the exact same point. It's right here. Okay, right here at the 0, 0. And in this case, the y-intercept is the cost of buying 0 chocolate bars. The cost of buying 0 chocolate bars. It's still 0, okay? So the number of chocolate bars you bought, or the x, is 0, okay? So in this context here, the y-intercept and the x-intercept represent different things. Along with this, what this also has, any linear function has a slope. Okay? Now you've used slope. You know that the formula for slope, it's rise over run, or it's y2 minus y1 over x2 minus x1, or there's probably a dozen other formulas, delta y over delta x. All sorts of things that you could do. You've used slope in science. In science, slope is like velocity is slope. If you've done physics or science 10, I think they still do it, where you do a series of points based on the position of this little cart. You can figure out how fast the cart is going. The slope represents the rate of change. And I want to put that right under here. It is the rate of change. In this context, if I calculated the slope, no matter how I did it, no matter which points I used, the slope would be 1.25. 1.25. Reason? Because it's going up by $1.25 each time. The rate of change. As I buy more chocolate bars, I'm going up by $1.25. The slope of this context is $1.25. It's the rate of change. In Math 10, we give you all these points and we get to use the complicated formulas and you do it. And it seems like it's mystical and magical somewhere along the line. But really, in all honesty, it's how much it's increasing by. And if there's a context, it often gives you the slope without coming out and bluntly saying, the slope is 1.25. It doesn't tell you that. It just makes that so you understand it. Okay? So you've got a slope. Along with this, in each of these contexts, and I'm just going over to the right, you've got a domain, and you've got a range. Okay? Now the domain and range causes people fits. People find the domain and range very confusing. We use like greater than symbols, less than symbols, that sort of thing to do domain and range. There are actually a whole bunch of ways to do domain and range. But the thing that's going to come up in this unit that probably didn't come up before is there's contextual domain and range and there's mathematical domain and range. And it depends kind of on what it's asking. Based on the context, the domain is all of the x values you can have. X is the number of chocolate bars. So based on the context, the domain, or the number of chocolate bars you can buy, has to be greater than 0. Greater than or equal to 0. Based on the context, and I'm going to put that right beside it, context. Because based on the context, the domain is greater than 0. Based on the context. It doesn't make sense to have negative chocolate bars. In theory, you could buy 6.2 trillion chocolate bars too, although I don't know where you're getting them from. But in theory, mathematically, anything greater than 0 makes sense. It means something. Okay? The context says that. The range, based on the context, the range is all the y's, or all the values you could be asked to pay. You will be asked to pay either 0 or more dollars for these chocolate bars. Based on the context, that's the range. And based on this context, that would be my domain and range. Based on the mathematics, if I was to just give you the graph exists forever to the left and forever to the right. So in that case, the domain would be x as an element of the reals. You remember this? And the mathematical range would be y as an element of the reals, because it exists forever to the left, forever to the right, forever up, and forever down. Pardon me?
You just like worded it different.
X is any real number? Yeah, that can be done. Yeah, x is any real number. The little e is actually the element symbol. It's a set theory symbol, believe it or not. But from there, you've got that. Now, both of these answers for domain, or both of these answers for range, are correct depending on what I'm asking. Okay? And that's the thing I need you to recognize, first off. Based on the context, there's certain legitimate things, and everything else doesn't make any sense. based on the mathematics, anything makes sense. So you have to kind of keep that clear. And the question will come out and say that. It tries to be as clear as it possibly can. For the purposes of in-class tests, ask me, is this context or math? I'll tell you. But it'll say something like, based on the context, the domain of this function would be. It's telling you the context. Okay? So you've got these. And any linear function has these. Okay? If I look at another example, e.g., here's one where things are a little different, but just to talk about. The number of liters of water in a tank starts at 100 gallons. Or sorry, 100 liters, I guess. Okay? So there's 100 liters of water in the tank. A plug is pulled and the water flows out at 7 liters per minute. Okay? So you've got that. If I want you to sketch this graph, this is a linear function as well. Okay? It's going to be a straight line. It's going to be linear. It's going to have then, because of that, one x-intercept, one y-intercept, a slope, a domain, and a range. Okay? And so from there, what you've got is you've got your grid. Now, for this context, it only makes sense to look in that top quadrant. This quadrant, and this quadrant, the three marked with the x's, they don't make sense. They're spots where either time is negative, so before you even started timing, which exists, I guess, but you didn't measure it, so you have no idea what happened. Or the volume in the tank is negative, which doesn't make any sense. How do you have negative 5 liters of water in a tank? It just doesn't make any sense. So from there, you've only got this straight line, and it only exists in this first quadrant. Okay? Now from there, it starts at 100. So at time 0, there were 100 liters of water in that tank. And from there, you can go and create all sorts of series of points. After 1 minute, there were 93 liters of water in the tank. Okay, because you lost 7. 7 flowed out. Now, I don't know where those 7 went. They just went down the drain. But nonetheless, there's only 93 liters of water in the tank. And I can go at 2 minutes, and there'd be 7 less, so there'd be 86 liters of water in the tank. And so on and so forth. I can go at 7 minutes, and I'm just randomly choosing points. And if I did the math, there'd be 51 liters of water in the tank. And so on and so forth. Now this isn't necessarily drawn to scale. But if I looked at this graph, I'd get a straight line. I missed that point, so I'm just going to make it bigger. Okay? I'd get a straight line that looks something like this. In theory, it exists all the way to the left. In theory, it exists all the way to the right. But it doesn't make any sense. There's no purpose in going any further than this x-intercept. Okay, that's the x-intercept. And that is the moment where the volume of the tank is 0. The y is 0. So there's no water. Okay, the x-intercept is where y is 0. The y-intercept is up over here, and that is where x is 0. Start timing. That's where I first looked at this thing. Okay, that's my y-intercept. And so I've got this. So in this context, my x-intercept and my y-intercept mean things. Do you understand how I'm getting these? Because I'm just thinking my way through this. Along with this, you know that it's got a slope. Now the slope is the rate of change. And I could get you to do it with rise over run, or delta y over delta x, or the y2 minus y1 over x2 minus x1, or any of those other formulas. But you know contextually that the slope is the rate of change. How much is this going up or down by? Well, it's going down by 7, so its slope is -7, or -7/1, which is what we made a big deal about, because we wanted it as a fraction, and you counted over and up or over and down, and you got other points. But really, contextually, I know this slope. It's -7. Okay? Then also, too, I've got domain and range. Now, domain and range can be done contextually or can be done mathematically. Mathematically, they're elements of the reals or they're any real number or whatever. So I'm not worrying about that. I'm going to do contextually, and I'm going to write context. But I can't just say greater than 0 or less than 0. Okay? I'm going to do the range first because I'm set and ready to do that one. The range. The y values that it exists for start up here at 100 and go down here to 0. There's nothing bigger than 100 and there's nothing smaller than 0 in that tank. You guys see what I'm saying? So the range is between 100 and 0. I've written that with the whole notation. 0 is less than or equal to y, it's less than or equal to 100. That is between 100 and 0. Now, that is kind of a really simple version of set notation. Really, in all honesty, if you did more sets, there'd be like brace brackets and things like that. That's all you need, and that's all you're going to see on the diploma. But it's between 0 and 100. For the x's start at 0, where I'm putting that little arrowhead, and they go to this spot. Now, I don't know what that spot is yet, but they exist anywhere from 0 to that spot. You guys with me so far? So when I start to do my domain, it's between 0 for the x's and that number. How am I going to find that number? Well, logic, I can look at the equation, I can do a variety of different things. And this is where you get into what do you know about these equations. Now, I'm going to come back to this. Okay? Please don't forget that. I'm going to put a little box here just to remember. I haven't done that yet. Okay? But ladies and gentlemen, I need to figure that out. Now, one way to do it, if I asked you to do it logically, I bet you could figure it out. If it goes down by 7, you just keep going. 2 is 86, 7 is 51, then 8 is going to be 44, and 9 is going to be 37, and you just keep going. And you may get to 0, and you'll get to 0 partway between something and something else. Because at some point you're going to get a negative value. You'll be like, well, it happened between 12 and 13 minutes, or whatever it works to be. Okay? Where I want to go with this is I want to just go back to the equation. With the equation you have, the equation we gave you in grade 10 is y equals mx plus b. And we harped at you a little bit that m and b were numbers. And we told you that m was the slope and b was the y-intercept. Okay? I'm going to change that wording a little bit. M is the slope, but it's the rate of change. Okay? It is technically a slope. But using a different word for it, I think, helps make sense out of it with the context. And b is the y-intercept, but using a different word for it, I'm going to say the starting amount. What you started with. In the case of the chocolate bars, the cost of 0 chocolate bars, I started at 0 and I counted from there. In the case of the tank, I started at 100 and I went down from there. So once I've got this done, I can go and use logic to create an equation. My equation for the last example is y equals the amount of water in the tank equals, I'm going down by 7, so my rate of change or my slope is -7 or -7/1. X is the number of minutes, and I started at positive 100 liters. I built the equation logically, and in fact, this is what you intuitively do anyway. You know this. This is my equation. From there, I can go back to figure out what I had before, and I'm just going to kind of put it off to the side, so I don't know where you want to fit it on your page. But I know that I need the x-intercept for the rest of that domain. So to find an x-intercept, I need to let y equal 0. So I have my equation, y equals negative 7x plus 100. I have two variables, x and y. I know y has to be 0. So I get 0 equals negative 7x plus 100. And I have to solve the algebra. Adding the 7x to the other side, I'll get positive 7x equals 100. And then I'll divide by 7. And what is 100 divided by 7? Do you guys have the answer? 14.2? 14.2857, da-da-da-da-da, that sort of thing. So it's 14.28-ish. Okay, dot, dot, dot. That's how many minutes it's going to take for the tank to be empty. At 14, I'd have water in it. At 15, the math would tell me that I'd have negative water in it, which makes no sense. It's going to take 14.28 minutes. This logically, right here, this logically is probably what you would have done if I just asked it to you and said, you know, you've got to figure it out. Most of you would take 100 divided by 7. But the algebra is supporting that. My equation is supporting that, and that's all that's going on. So since it takes 14.28 seconds, my domain would be between 0 and 14.28. That's based on the context. Does this kind of make sense? Okay. Now, linear functions occur in lots of different things, but they all kind of look like this whole, and I'm putting it in a little cloud here. The y equals mx plus b, which honestly, if you ask a lot of parents, what do you remember from math from school? If they haven't done math in a while, they'll be like, well, I remember Pythagoras, a squared plus b squared equals c squared, and I remember y equals mx plus b. But hell if I remember what it means. That's what happens. Y equals mx plus b probably stuck somewhere in your brain, and you know that. This is what's going on. M is your slope or your rate of change. B is where you started with. And so you can use that to do all sorts of contexts. Okay? If I look at this one here, okay, e.g., to host a banquet, a caterer charges a $65 setup fee. Whoops, I don't know why fee, okay, plus, I'm just going to make nice round numbers, $10 per person. Okay. Now, I haven't asked a question for this yet. But this is, I mean, I'm making up the numbers, but a lot of times if you get catering, I mean, I catered my wedding a couple of years ago. Okay? They charge a setup fee, plus they charge so much per person for whatever food you get. Now, $10 per person is actually really cheap. If you could get a caterer that charges $10 a person, just hope that the food is edible. Okay? But ladies and gentlemen, from there, this is a linear relationship. And so you can use this logic, and I could ask part A, what is an equation? Okay, I'm just going to write what is an equation. And so if I want an equation for this, I could use y equals mx plus b. Now, just like when we had back in the exponents and logs stuff, you don't have to use y and x. You can use whatever letters you want. But y equals mx plus b is the theory. So I'm going to say the cost of hosting the banquet. I'm going to come up with a letter for cost. I'm going to call it C. So the cost of this banquet, I don't care if you use y or x or whatever. Okay? I may use a particular letter. It may not be the letter you use. You may not want to use the letter S or C. You may want to use W. I don't care, whatever letter you want. But the cost of this banquet, okay? $65 setup fee, $10 a person. $10 per person is my rate of change. Every time I add a person, it goes up by 10. Every time I add a person, it goes up by 10. So my slope is positive 10. X is the number of people. I'm going to write P for people because I want to change the letters. And B is going to be what I started at. It cost me $65, so I'm starting at my $65 amount. These are linear functions. And I can, if I take the context out of them, it makes a whole lot less sense. Because that's what happens in 10C. We take the context out. We're just like, plot this point, plot these points, plot these points, da 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 da. We get you to do slopes and equations and all this jazz. If we remove the context from it, it becomes more complicated. But really, if you put the context into it, it makes a lot more sense. From here, now once I have the equation, I could ask anything. Okay, B. How much will it cost for my wedding? There were 34 people. Okay, I had a small wedding. Okay, so how much will it cost for 34 people? Well, once I have the equation, I can use the equation. Keep in mind you've got two unknowns, X and Y, or in my case, C and P. C is the cost, P is the number of people. I don't know C, but I do know P is 34. So I have my equation, which is C equals 10 times P. P is 34, plus 65. Without the equation, honestly, this is what you would have done anyway. You would have done 10 times 34 plus 65. You understand the equation. And if you do that, you're going to say, okay, it cost, I think it's $405. If I'm wrong, please let me know. Okay? But ladies and gentlemen, for my 34 people wedding, it's going to cost, at this price, $405. Okay? And I can ask other questions too. If I have $1,000 to spend, how many people can I invite? That sort of thing. Okay? That, in that case, you'd have to round down. Like you can invite 28 or 282.7 people. Well, for $1,000, you can invite 282. Okay, you're just using logic. I can't invite 283 because I'd be over my $1,000. Does this make sense? Okay, ladies and gentlemen, I can do lots of these equations. Now, if the context is given, you can do that. I've got another example that I'm not going to do. It talks about a car traveling 87 kilometers per hour. Okay, if I'm traveling 87 kilometers per hour and I start 200 kilometers from Red Deer and I'm traveling towards Red Deer, I want an equation. The slope would be negative 87, all that jazz. But where I want to get to now is linear regression. Okay? Linear regression. Okay? The calculator does regression. You know regression is calculated a line of best fit or an equation of best fit or a curve of best fit. Okay? Ladies and gentlemen, here's an example. E.g., we know the following. And I'm going to give you a table. I'm going to put it on the left. Degrees Celsius, table, degrees Fahrenheit. You know that they are not the same. If you don't, turn on an American news channel and watch the temperature, and they're going to tell you it's going to be 87 degrees. No, that's a nice day, but no, it's not going to kill you. Okay? 87 Fahrenheit is something else Celsius. Okay, you know this. My parents, at any rate, probably your grandparents, honestly, are comfortable. My parents still think in degrees Fahrenheit. Their thermostat is set in degrees Fahrenheit. 68 degrees Fahrenheit. That's what their thermostat is set at. Okay? But we know certain things. 0 degrees Celsius is 32 degrees Fahrenheit. 100 degrees Celsius is 212 degrees Fahrenheit. The spot where they're the same, minus 40 degrees Celsius is minus 40 degrees Fahrenheit. 40 below is 40 below. Okay. Once I have a series of points, if I want an equation, okay, I can use my calculator. I've got these points, okay? So I'm going to go to my calculator here. I'm going to push stat. Okay, can you guys get out your calculators just to follow along? Stat. I'm going to go edit. Anything in here, clear it out. So clear, enter, clear, enter. So clear out your L1 and L2. But I'm going to put that in. Now using this data, okay, I know that 0 degrees Celsius I can't type it. It's frozen. My program has frozen. Okay, 0 degrees Celsius. I've got 100 degrees Celsius. I've got minus 40 degrees Celsius. I can go over to my L2 and I can say, okay, 0 degrees Celsius is 32 Fahrenheit. 100 degrees Celsius is 212 degrees Fahrenheit, and minus 40 is minus 40. And once I've got this data in, I can get it to come up with an equation. So keep in mind, I do stat, you did regression before, go over to the right. Here's where exponential and linear or logarithmic regression were. Linear regression is LIN. It's option 4. Now you can see it, the calculator doesn't use mx plus b, the calculators use ax plus b. It's just different letters. A is still your slope or your rate of change, b is still your starting amount or your y-intercept, so you can go from there. So I'm going to run my linear regression. Now I just choose that one instead. Keep in mind the 84s, I have to scroll down to calculate, 83s I just hit enter. But ladies and gentlemen, it gives me my equation. Y equals ax plus b. A is 1.8, B is 32. So I can go through to what I've got, and my calculator tells me that Y equals 1.8x plus 32. Okay? And this is an equation that links rate of change, or degrees Celsius to degrees Fahrenheit. You have to keep in mind, whatever you put in L1 is your X, whatever you put in L2 is your Y. So since I put degrees Celsius in my X, X is degrees Celsius, and my Y is degrees Fahrenheit. Okay? Now you can rewrite it with whatever letters you want, but I've done the linear regression. I've got this equation now that works. And from here, I can say, okay, I can ask anything, okay? My parents keep their thermostat at 68 degrees, so I've done the regression to create this situation. A, okay, what temperature is 68 Fahrenheit, 68 degrees Fahrenheit. Okay. What temperature in degrees Celsius? Okay, my parents set 68 Fahrenheit. What is that temperature? Well, so you've got your two variables, your X and your Y. Okay, you can change the letters if you want, but keep in mind the calculator uses that. I've given you Fahrenheit, so that's Y. So I'm going to say Y is 68, X is unknown. I'm going to use my equation. 68, or Y, equals 1.8x plus 32. I got to use math.
How do you know
Honestly, whatever you put in your L1 is the X, and whatever you put in your L2 is Y. Okay, so you have to pay attention when you put these things in. Since when I went into my calculator, I put that in L1 and that in L2. That's how I know. Whatever's in L1 is X, whatever's in L2 is Y. Okay, if I did it the opposite way, I'd get just as useful an equation, but X and Y would be swapped. Okay, from here I got to solve this, so I'm going to subtract the 32, subtract the 32. 68 minus 32 is going to be 36, I think. Equals 1.8x. Divide by 1.8, I'm going to get x is equal to 20. So 68 Fahrenheit is 20 degrees Celsius. You can use this equation to do any sort of conversion, anything like that. If you wanted it to be set up to work the other way, you just switch the x and y's, but your x and y would be switched. Okay? You can do this linear relationship, Celsius Fahrenheit. That's a linear relationship. There are lots of linear relationships. Okay? If I was to do another linear relationship, e.g., okay, currency exchange is a linear relationship. Okay? So if I look at currency exchange, okay, so if you do currency exchange, all you need is a series of points and you can create an equation. Any of those online calculators, all it does is use the equation. Now with currency exchange, it changes every day. Okay, the equation changes. Today's equation is different than tomorrow's equation and all that jazz because of how it floats on the different stock exchanges. But ladies and gentlemen, I did some research. Australia has dollars. Okay, Britain has pounds. Pardon me?
That's so cool. You said my name and I was like, what?
Oh yeah, sorry, I never thought about that. The British pound and the Australian dollar, I never thought about that. Okay, so ladies and gentlemen, I went and did some random research. And according to the online calculator today, okay, 220 Australian dollars equals 117 pounds and 64 pence. Okay. Now, different currencies have different amounts and different denominations, but nonetheless, you can say that. I did another one that said 860 Australian dollars equaled 459 pounds and 88 pence. And I did 1,700 Australian dollars equals 909 pounds and 7 pence. Okay? And so you've got this relationship. Now, in theory, you can end up with an approximation. And you can do any currency to any currency. The example I wanted to put was the Israeli new shekel to the Iranian real. But I did realize that would probably be confrontational. But nonetheless, you've got this. From there, you can create your equation. Okay? Y equals something x plus something. Okay? All you need to do is put this data in. Keep in mind whatever x is in L1, whatever y is in L2. I'm going to put Australian dollars in L1, British pounds in L2. You just have to keep that in mind. From there, you go to your calculator and type it in. So if I go to my calculator, stat, edit, okay, clear out what's in there, clear, enter, clear, enter. Okay, I've got 220. I've got 860. I've got 1,700. And for the equivalent British pounds, I've got 117.64. I've got 459.88. And I've got 909.07. So I put that in. Once I've got that in, stat, over to calc. I run the regression I want. In this case, I want a linear regression, LIN. Keep in mind, LIN is linear, LN is natural logarithmic. So I'm going to run linear regression, and I'm going to scroll down, and I hit calculate, and it gives me my equation. A equals 0.53475, and B equals negative 0.05. So from there, okay, I've got y equals, I forgot the numbers already, 5.3475, so 0.54375, and B is negative 0.05, so negative 0.0, is it 05 or 005? I forget. 005. And once you've got the equation, you can do any sorts of questions. Keep in mind you've got two variables, y and x. Okay, you can change the variables if you want, and you can ask questions. Does this make sense? Okay, that's the end of this lesson. Before I do anything else.